that before you start.
The intro will take a few minutes.
No, but still, whether he's going to start, we should not have a gap after the intro. Then maybe I will have to pitch in or something.
Yeah.
Maybe before you start. I just call in.
The intro will take a few minutes.
Okay. Okay. Hello? Okay. So the intro will take a few minutes. So once the Zoom is ready, you just come in. Okay, sir. It's our bad luck. Don't worry. Okay, sir. Good.
Gauri, you can start.
Good evening, everybody. From the Tamil Heritage Trust, we are extremely happy to welcome all of you to the May 2025 edition of our monthly talk series. I think most of us are aware of the fact that the ancient Indian texts were written largely in verse form, and they were passed on from generation to generation using the oral tradition. The source texts for in ancient Indian maths and ancient Indian astronomy also belong to this category. A natural question which comes to our mind is, how were numbers represented under this genre or in this scenario? You'll be surprised to know that the ancient Indians had a highly evolved and scientific method for representing numbers, or what they have called as numeration systems. They basically used linguistic phrases, which were either in the form of syllables, words, or a series of sounds to represent numbers. And this was used both in the verses as well as the commentaries, which were written in prose. Several systems of numeration were there at that time. Some of these include bhūta-saṅkhyā, bhūta-saṅkhyā, kaṭapayādi, Āryabhaṭīya, etc. A lot of research has been done on these systems, and these are well written about, both in scientific journals as well as ordinary books and popular articles. What many of us are not aware of is that there was a lesser known system which was used essentially in the Tamil astronomy tradition. This has been found in a book called Cūḍāmaṇi Uḻḷamuḍaiyān, written around 12th to 13th century by somebody called Tirukkoṭṭiyūr Nambi. In this text, we find that they were using vowels, or what they called Uyirēḻuttu, for representing numbers, and this system is quite different from the systems that I mentioned earlier. We are fortunate with us to have three eminent scholars who have done a lot of research on Tirukkoṭṭiyūr Nambi's work and will be enlightening us about the texts contained in the Uڵḷamuḍaiyān Cūḍāmaṇi. A very warm welcome to Dr. V Ramanathan from IIT-BHU, Dr. Venketeswara from IISER Pune, and Professor MD Srinivas from CPS Chennai, who will be giving us an enlightening talk today about how numeration system followed in the Tamil astronomical tradition. Hello, sir. We are extremely happy to have all of you here. Before we move on to the main program, let me give you a brief introduction about Tamil Heritage Trust, which is our organization, especially for the benefit of those who will be joining us for the first time today. Tamil Heritage Trust, or Tamil Paramparya Arakattalai, is a non-profit voluntary organization started by a group of like-minded people almost 14 years back with the explicit objective of understanding, appreciating, disseminating, and celebrating information related to India's rich history and heritage, not just for the benefit of those who are academic and scholarly minded, but for the average public as well. Towards this end, THT conducts programs throughout the year. Chief amongst these are talks and seminars. Our most popular program is the monthly Heritage Talk, and as I already mentioned, we are in the midst of the May 2025 edition. We are extremely proud to say that we have conducted this program almost uninterrupted for 14 years now. We merely changed the format from in-person talks to online through and post-Corona. Another event that we conduct is called the Indology Festival and is conducted in the month of June. This is an annual online event and is more scholarly in nature, where across 6 days, we have 12 experts and scholars coming together to discuss a particular topic from an academic and serious point of view. A third event that we have is called Pechu Kacheri or Oratory Concert, which is conducted in the month of December to collaborate and coincide with the Margazhi Isai Kacheris of Chennai. This is an in-person event conducted across 2 days where we have 10 to 12 talks on a particular topic. We are extremely happy to say that our Pechu Kacheri in December 2024, called Tolliyal Kapiyam, Archaeological Expeditions in Tamil Nadu, was a huge success, both from the point of view of the audience as well as the speakers. Apart from these talks and seminars, we also have workshops and classroom sessions on and off. We have one-day workshops called How to See a Museum, How to See a Temple, etc., which are conducted in 2 sessions. In the forenoon session, we have a series of lectures, and then in the afternoon session, the participants are taken practically to a site where we elucidate upon what was discussed earlier. Anybody can register and join and participate in these sessions. Then on and off, we have classroom sessions also on a variety of topics like ancient Indian astronomy, ancient Indian mathematics, Grantham script, etc. Another initiative of ours is called Alambar Avai, where the target audience are the school teachers of Tamil Nadu. Over a series of weekend lectures, various aspects of Indian history and heritage are discussed with these teachers, the idea being that they take them back to their students, thus further spreading awareness. Docent training is another initiative of ours, and we are extremely happy that version 2 of this was completed only recently. 30 people graduated from this session, and they are ready to present historical sites and historical monuments in a professional manner to the enthusiastic audience. We'll be launching version 3 of this session very soon. Site seminar is another initiative of ours, which is in-house and largely meant for our own self-education and self-enhancement. This is conducted in the month of January every year. We normally zero in upon a particular site in India, and our volunteers study this in detail over several weeks. We have quite a few number of in-house seminars, and then armed with all this knowledge, we visit these sites and experience it in its totality. We also try to come back and document what we have seen. In January 2025, we had visited various areas in and around Gwalior and Jhansi, belonging to the slightly lesser known Kaṭapayādi dynasty. From Tamil Heritage Trust, we have also instituted 2 awards. The first such award is called THT Professor S. Swaminathan Heritage Award and is given to an individual for their contribution to Indian history and heritage in an individual capacity. Last year, this award was won by architect Madhu Voteri for her extensive contribution to popularizing Indian heritage amongst the youth of Hyderabad. The second award that is given by us is called V Venkayya Epigraphy Award and is given for individual contributions in the field of Indian epigraphy. Named after V Venkayya, who was the first official Indian epigraphist, this award has been instituted by Miss Sunita Madhavan, his great-granddaughter. THT has been entrusted with the responsibility of administering this award. Last year, this award was won by senior epigraphist V Vedachalam, who is retired from the State Department of Archaeology, Tamil Nadu. We are in the process of inviting nominations for this award for the year 2025. We have a dedicated YouTube channel where you will find links to all our past talks right down to this talk going on today. Kindly subscribe to the channel and click on the bell icon to receive notifications of future events. These are our social media handles, and this is our mailing address. You can mail us here to either join our mailing list or to contribute in any way to our activities in a voluntary capacity. We are a non-profit voluntary organization So any kind of financial contributions are welcome. You may use this QR code or this address to contribute generously, and it will be greatly appreciated. That in a nutshell was about THT. Now moving on to today's talk. As I already mentioned, our speakers will be examining details of using Uyirēḻuttu, vowel-based numeration scheme as explained in the Tamil astronomical work Cūḍāmaṇi Uḻḷamuḍaiyān by Tirukkoṭṭiyūr Nambi. This work is supposed to have been written in the 12th, 13th centuries. In particular, our speakers will be explaining how the system was used in encoding lunar longitudes and its application in the formulation of the 248 Candravākyas, which are also referred to as Pañcāṅgavākyas in Tamil. Before I hand over the screen or stage to them, I'll give you a brief introduction about our speakers. Dr. V Ramanathan is a physical chemist in the Department of Chemistry at IIT-BHU, Varanasi, and heading their IISER center. He carried out his postdoctoral research works in the University of Stuttgart in Germany, University of Basel in Switzerland, and Seoul National University in South Korea. He obtained his PhD from IIT Kanpur, India. His areas of current academic research are Raman imaging and spectroscopy, SERS, and computational chemistry. His other research interest lies in studying the scientific heritage of India. He is a Fulbright scholar and a former core committee member of the Indian National Young Academy of Science, a body of Indian National Science Academy, IISER. Dr. Venketeswara is a scholar, is a renowned scholar in the field of Indian mathematics and astronomy with expertise in Sanskrit scientific literature, manuscript studies, and traditional knowledge systems. As a faculty member at IISER Pune, he has made significant contributions to the study of historical mathematical texts, their interpretations, and their relevance within the broader framework of Indian knowledge systems. He has done extensive research on Indian astronomical treatises, making use of his strong background in philology and with mathematical analysis and computation. Dr. Pai has authored numerous articles in peer-reviewed journals and books, receiving prestigious awards for his research in Indian astronomy and mathematics. Dr. M.D. Srinivas, a Padma Shri awardee of 2025, is chairman of Center for Policy Studies at Chennai, a research institute which he founded along with Dr. J.K. Bajaj and a few colleagues with the objective of comprehending India from an Indian perspective. After completing his PhD in University of Rochester, New York, Srinivas taught at the Department of Theoretical Physics, University of Madras, between 1976 to 1996. His areas of interest are conceptual and mathematical foundations of quantum mechanics, Indian scientific tradition, especially Indian mathematics and astronomy, and society, polity, and economy of India in the 18th century. He has published significant works in all these fields. He was selected a Fellow of Indian National Science Academy in 2023 for his work on history and philosophy of science. Without further ado, I invite our speakers to take over the stage and deliver their lecture today. I'll stop sharing and I'll bring on their main presentation.
Can Ramanathan go on a video? Yes.
Shall I?
Yeah.
Should be.
You can go full screen.
Yeah. I've done. Yeah.
Yeah, Ramanathan, you can start whenever you want the screen to be changed. You can just call for it, and Gauri will change the screen.
Yeah. Thank you. Thank you very much. Namaskaram to one and all. And at the outset, I thank the Tamil Heritage Trust to have given us this opportunity to present our work, which is titled Uyirēḻuttu, that is Tamil vowel-based system of numeration used in Tamil astronomy texts. It is my proud privilege to be part of this team, which comprises of Dr. Venketeswara Pai as well as Professor M.D. Srinivas. And the work that we are presenting today is in press in the journal, Indian Journal of History of Science. Next. So I will be starting this talk where I'll be taking you through this bhūta-saṅkhyā system, Āryabhaṭīya system, and kaṭapayādi system, which are the key systems of numeration, very well researched, used, popular in the Indian astronomy. Thereafter, I will be introducing this Uyirēḻuttu or vowel-based numeration scheme, and that will be followed by use of Uyirēḻuttu-based numeration scheme in Cūḍāmaṇi Uḻḷamuḍaiyān, Tamil Astronomy text of 12th, 13th century. Then it will be followed up by Tamil Candravākyas or Pañcāṅgavākyas. Then it will be followed by a presentation by Dr. Pai, where he will be giving substantial example for the concept that I'll be introducing. Next one, please. So when we talk of systems of numeration to represent numbers in the text, it is indeed a no-brainer that the decimal place value system, which originated in our country, has been the gift to the world, and world over this has created a big revolution by which computations became easier, and to this day we are harping the benefits of it. On one side, when we use characters like 0 to 9 to represent these decimal numbers, in our Indian tradition, there has been a system of using words, phrases, or sequence of syllables to denote numbers. And these systems were used extensively in all the texts, especially of astronomy and mathematics, which were composed in the form of sutras or metrical verses called vrittas, which of course enabled these texts to be committed to memory by all students and scholars, because unlike today, where we have the ability to outsource the memory to a device, back then the brain or the human brain was the only seat of memory. So whatever aided this, the metrical form aided the memory, and the words when used for numbers became a good aid for that. So such system of numeration were also used to develop linguistic mnemonics for remembering tables of sign values, particularly in the aspect of astronomy and various other astronomical parameters, along with other mathematical and physical quantities of interest. So the three basic scheme which were employed to write words for denoting numbers were bhūta-saṅkhyā, Āryabhaṭīya, and the kaṭapayādi system, which I will briefly try to introduce in the next few minutes. Next, please. So the word bhuta denotes element in the Sanskrit language, and this is used to employ word names for the digits from 1 to 9, and sometimes even larger number like 12, 25, or 27. So for this, use was made of names of objects or concepts which had a fixed number associated with them, either in nature or in our tradition. For instance, the words for eyes or hands do get naturally associated with the number 2. Vedas will be associated with the number 4. Ritus or seasons will be associated with the number 6, so on and so forth. The use of such words for denoting numbers can be seen occasionally in the Vedic corpus as well, but more often in the sutra and other literature, like the Shrauta Sutra of Katyayana and Latyayana, where we see instances of the words like Gayatri being used to denote the number 24. Similarly, Jagati being used, the word Jagati being used to denote the number 48. So such word names for numbers are used also extensively other than the astronomical text. In another text where they are used is the Chanda Shastra or Chanda Sutra by Pingala, where which the whole text incidentally discusses many of the combinatorial aspects of organizing and counting meters of a given number of syllables. So the following example, this is name of 1 meter or a chandas called Shardula Vikreditam, where Pingala uses bhūta-saṅkhyā to denote the caesurae or the pause. So Shardula Vikreditam Sau Tau Gaditya Rishayah. So Aditya and Rishayah are actually the two words here denoting the numbers 12 and 7. And in this definition of Shardula Vikreditam, these are to be understood as the pause to be given after 12 letters and thereafter after 7 letters. So that's how this has to be understood, and this is how bhūta-saṅkhyā seems to be employed here. Next. Next, please. So this is a table which summarizes the number as well as the corresponding words. So the number 0 is represented by words that denote sky. So kha and all its synonymous words like akasha, ambara, purna. Purna is not a synonym for akasha, but purna is also used, another word for denoting the number 0. Similarly, chandra or moon is used for representing the number 1, and all its synonyms that we can find in the dictionary entry can be used for representing the number 1. So on and so forth. You can get to see here from 0 to 9 how various Sanskrit words are used for representing the numbers. Next, please. So here is one example that we get to see its use in a text called Siddhanta Shiromani by Bhaskara II, where in one of the opening verses he says, Rasaguna Purna Mahi Sama Shakan Ripa Samaye Abhavat Mamotpattihi Rasaguna Varshena Maya Siddhanta Shiromani Rachitaha. So the words highlighted in red here are Rasaguna Purna Mahi Sama. So which is actually standing for the word for the number 1036. And in our tradition, the numbers are written or placed from right to left. Even though we read the text from left to right, one must keep in mind that the numbers are so arranged in the increasing order of 10 from right to left. So that must be kept in mind. So even if it is read, Rasa is standing for 6, Guna for 3, Purna for 0, Mahi is for 1. Mahi means earth, earth is 1. So even though it is written in Rasaguna Purna Mahi, this stands for the number 1036. Similarly, the next line, Rasaguna Varshena Maya Siddhanta Shiromani Rachitaha means by the time I was 36, I completed this work called Siddhanta Shiromani. So 36 is denoted by the word phrase Rasa Guna. Again, Rasa for 6, Guna for 3. So it is 36. Next, please. There are interestingly instances of this bhūta-saṅkhyā per se used in Tamil as well, where we see Urukulam, Īrinam, Muttamil, Nanmarai, Ainpulan, Arusuvai, Yēlisai, Enpakkam, like etc. being used exactly in the same sense how bhūta-saṅkhyā has been used in Sanskrit. This is also instances seen in the case of Tamil. Next one, please. Next, we briefly introduce this Āryabhaṭīya system, where the Sanskrit Varnamala from Ta to Ma, which forms in the 5x5 grid, is given continuously the numbers from 1 to 25, and thereafter the Avargakshara, which are from Ya to Ha, they are getting the numbers 30 to 100 in the increment of 10. So with this consonant mapping to the numbers, the key role played in the Āryabhaṭīya scheme is the vowels, the Sanskrit vowels, where the A or A would stand for 10 to the power 0. Similarly, E and E would stand for 10 to the power 2. Similarly, as shown in this table here. This will be clear with an example, which will be coming in the next slide, please. Like this is the from the Āryabhaṭīya, where the revolutions of sun and moon are given. Yugaravi Bhaganaha Kyugru, Shashi, Chayagi Gushrutshulr. So the Ravi's revolution is given by the number Kyugru, by the word Kyugru, which stands for the number 43,20,000. Because Q stands for 32 into 10 to the power 4, and Gr stands for 4 into 10 to the power 6. So together, this will stand for 43,20,000. So like this, Āryabhata had invented this scheme called Āryabhaṭīya, and tradition has it that he is the only one who has used this scheme for the astronomical works. Followers after him, for some reason, they have not adopted this Āryabhaṭīya scheme. Rather, they have adopted either the bhūta-saṅkhyā and or the kaṭapayādi scheme very extensively, which will be introduced in the next slide, please. See, in the kaṭapayādi also the consonants are mapped like this, but the mapping to the numbers are slightly different from Āryabhaṭīya. The Kādi-nava, as the name implies, kaṭapayādi. So Kādi-nava, so it is ka, kha, ga, gha, nga, cha, cha, ja, jha, gets the number 1 to 9, and the nya gets the number 0. Similarly, Tādi-nava gets the numbers from 1 to 9, and the terminal na gets 0. Pa, pa, ba, bha, ma gets 1 to 5. That's the Vargakshara. Then Avargakshara again starts from 1. Ya is 1 to all the way to ha, which is coding for the number 8. In the kaṭapayādi scheme, it is the consonant which carries the numeric value, and vowels do not play any role in this case. In the sense, whether it is ka, ka, ki, ki, ku, ku, ke, kai, ko, kau, or kr, all these things would represent the number 1, no matter which vowel this ka is associated with. So in a way, there is a lot of degree of freedom that we can play around by associating any vowel to this consonant. Next slide, please. So the first ever occurrence of this kaṭapayādi scheme is seen in the work called Grihachara Nibandhana, a 7th century work by Haridatta, who uses the linguistic phrases to denote numbers which are given in parentheses. Like, say, for instance, he gives the word yuddha, and he also gives the number 91 immediately in the parentheses following that. And actually, if you see, yuddha, ya would stand for the number 1, and dha would stand for the number 9. It is here one must note that in the kaṭapayādi scheme, if there are conjoined consonants, the consonant that is associated with the vowel will only be taken into account, and those consonants which are not associated with any vowel are to be ignored. And if a vowel occurs independently, that is mapped to the number 0. By the way, the first instance of kaṭapayādi is seen in the Vararuchi's Vakyas as well. So here the word yuddha, even though half the appears, it is not of any numeric significance. It has to be ignored. And that's why U is taken and Tha is taken, which will code for the number 91. Then Anuna Jnana Tunga, this would code for the number here, where actually the consonant are only G and Tu. So G would code for the number 3 and Ta for the number 6. And remaining everything, like independent vowel or na or nya, all these things are coding for the number 0. Similarly, Kala, Ka is for 1, La is for 3, and that Kala is coding for the number 31. Next, please. In the Vakya system, we see the Candravākyas given completely in the kaṭapayādi code. So these are some Vakyas that I am showing here. The first 3 Vakyas, namely Girna Shreyaha, Dhenava Shrihi. And as you see, the letters and the numbers are color coded. So the Vakya Girna Shreyaha, it not only has got some linguistic meaning, it is over and above that linguistic meaning, it is coding here for the numbers 3, 0, 2, 1, which must be understood as 0 Rashi, 12 degree and 3 minutes. Similarly, Dhenava Shrihi, this is coding for the numbers 9, 0, 4, 2, which in turn is representing the longitude 0 Rashi, 24 degrees and 9 minutes. And the third Vakya, that is Rudrastu Namya, this is 22601, and hence this is representing 1 Rashi, 6 degree and 22 minutes. So between in the kaṭapayādi scheme, when the words are formed for denoting the numbers, they usually carry the linguistic meaning also. Unlike the Āryabhaṭīya scheme, where even though we form a word like say kyugr, it need not necessarily have a linguistic meaning. It only will stand for use. It is only used for representing the numbers. Next slide, please. So Vakyas, in general, the astronomical tradition of our country is based on either the Siddhanta and other one is based on the Vakya. In the case of Vakya, which originated in the southern part of the country, starting from Vararuchi, these are simple mnemonics to remember and then go ahead with the computation. So Vakyas are linguistic phrases, and Candravākyas of Vararuchi are linguistic phrases which serve as a mnemonic to represent the true longitude of the moon over a period of 240 days. The period of successive conjunction of the moon and its apogee is called an anomalistic month, which is 27.55 days on an average, and hence 9 such anomalistic months will make up to 248 days. Now, the Vakyas that I had shown before will be used to get the true longitude of the moon. So if the true longitude of the moon and its apogee are the same and given by lambda on some day at some time, then the true longitude of the moon on the next 2 days at the same time will be given as lambda plus 12 degree 3 minutes, which comes from the Candravākya Girnashrayaha. Similarly, the second day's longitude will be given by lambda plus 24 degree 9 minutes. So that is given by the second Dhenava Shri Candravākya. Next slide, please. Now we get to see the spread of kaṭapayādi, although it originated in Kerala, we get to see the spread of it in other parts of the country. I am taking about, I'm going to show some instances about its spread in Tamil Nadu particularly, where we see that Suryadeva Yajvan, who hailed from Gangaikonda Cholapuram, also from Tamil Nadu, mentions in one of his works the date of his birth as Vijnana Deeptashayaha. That is the one whose aspirations are illuminated by his knowledge, even though it carries a linguistic meaning. But more importantly, it stands for the number 15,68,004, which indicates the elapse of the civil days from the commencement of Kali. Similarly, in this Kamakshi temple of Kanchipuram, we see a record of the gift of a copper door by Harihara II, where it is written as Shaktya Loke Shakabde. So this Shaktya Loke stands for the year 1315 in the Shaka era, which translates to 1392 or 1392-93 in the Gregorian calendar. So another inscription in Satyamangalam in the Vellore district has got a kaṭapayādi code, where Tattva Loke Shakasyabde. So here Tattva Loke is in the kaṭapayādi code to represent the year 1346, which translates to 1424 in the Gregorian system. Apart from that, there were Tamil astronomers settled in predominantly various parts of Tamil Nadu, and particularly we see records of them in Pondicherry, who were using this Vakya system of astronomy and were continuing this Vakya tradition. Next, please. The other place where kaṭapayādi is extensively used, non-astronomical, non-mathematical place, is in Carnatic music, where we see the Melakarta ragas, be it in the Asampurna scheme or in the Sampurna scheme. The ragas are named in such a way that the first 2 letters are having the kaṭapayādi code. In fact, the arrangement in the of the 72 also incorporates a bhūta-saṅkhyā, when the 72 is divided into 12 chakras, and each chakra has got a name which is having the bhūta-saṅkhyā code. So it is the Indu chakra, Netra chakra, Bana chakra, Agni chakra. So Indu is 1. So the first chakra is the Indu chakra. And the kaṭapayādi thing comes in the first 2 letters of the raga's name. Take for instance, Maya Malava Gaudai. Ma would stand for the number 5 and Ya represents the number 1. So this Maya would stand for the number 15. And lo and behold, the Melakarta number for Maya Malava Gaudai is number 15. So if we take the second raga, which is Ratnangi in this Sampurna Paddhati, or Phenadhyuti in the Asampurna Paddhati, both actually would quote for the number 2 as per the kaṭapayādi scheme. Next, please. Now, as I said, there were Tamil astronomers who were well versed with the Vakya scheme that has been practiced in the Sanskrit world, in the Sanskrit language. But the Tamil astronomers had difficulties in directly importing the kaṭapayādi scheme in the Tamil language per se, because of the obvious absence of the central 3 letters. So Tamil syllables are only ka, nga, cha, nya, tana, tana, pama, yaralava, yala, rana. So the absence of these 15 letters would make kaṭapayādi non-compatible with the Tamil script or the Tamil letters. So this prompted the next one, please. This prompted, or this gave an ingenious way for the ancient Tamil astronomers to come up with a unique scheme, which is based on purely on the Tamil vowels. And that's why we call it as a Uyirēḻuttu numeration scheme, where each of these vowels are mapped with the numbers from 0 to 9, as it is shown in the table in the screen here. So each vowel, whether it appears independently or with a consonant, will code for the number as given in the table above. Independent consonants that are not associated with any vowel are to be ignored. The numbers associated with the successive individual syllables in a linguistic phrase are to be placed from right to left in order to get the number denoted by the phrase, which is a practice as we saw it in the case of kaṭapayādi as well as bhūta-saṅkhyā. That is, the numbers are written or placed from right to left. Next, please. Next, please. This scheme would be more clearer with an example. Say we take the word parahitam. So I have color coded this parahitam with the number where the word with the letter pa is, since it is associated with the vowel a, it is coding for the number 1. Ra is associated with a and hence 1. Ha is associated with e, so it is denoting the number 3. Ta is associated with a, so it is number 1. The terminal im is independent consonant. It is not associated with any vowel, so it has to be ignored. Hence, the word parahitam in the Uyirēḻuttu scheme would stand for the number 1311. Similarly, the word Uڵḷamuḍaiyān would stand for the number 29,515. And here we see 2 consonants which are not associated with any vowel, il and the terminal in. So they must be ignored. They do not carry any numerical value. Next, please. The word Ilangovadigal would now stand for the number 13,1013. And here we see that the ing and the il are independent consonants, so they are to be ignored. So this way, this Uyirēḻuttu scheme is to be understood and used. Next slide, please. But at this must be also taken very seriously that the practice of representing number using Tamil script or its modified version, which has been in vogue for quite some time, is not the same as a numeration scheme. This, the representation that I'm showing in the table, which you see, the letter Ka is for 1, U is for 2, modified Ng is for 3, like that. This is like a Roman number representation, where the word, the letter X is used for 10, B is used for 5, capital I is used for 1, so on and so forth. The representation must not be confused with the numeration scheme. And this representation has got some antiquity because the Tamil community is quite familiar with this famous encounter between Kambar and Avvaiyar, where Kambar chided Avvaiyar by asking a puzzle, Oru kaaladi, naalilai pandaladi, and the retort given by Avvaiyar to Kambar, she begins the retort with Etteha Lakshaname, where she actually wanted to call him Avalakshaname to represent a va she uses ettehal because a stands for 8. So 8 will denote a, and 1/4 is represented by va. Hence, ettehal lakshaname would actually become avalakshaname. So this way of representing number using modified Tamil script or the script per se is not same as a numeration scheme that we are trying to talk here. Next, please. Now, where do we see this numeration scheme in action? We see in this text called Cūḍāmaṇi Uḻḷamuḍaiyān, and we get to see this one of the earliest editions of this Cūḍāmaṇi Uḻḷamuḍaiyān. A part of it, namely the 8th and the 9th chapter, is seen in a book called The Oriental Astronomer, edited by Huizington, who was working in the seminary at Betikotta in Jaffna, Sri Lanka. He publishes it in 1848. Subsequently, we have a version along with its commentary by Āryabhaṭīya in 1861, which is edited and published, which we have an access to by Gurulinga Deshikar in the year 1927, which is again with the verse as well as the commentary. And as on today, the latest critical edition that we have is by Dr. Satyabhama Kameshwaran in the year 2007, published by the Tanjavur Saraswati Mahal Library. Next, please. So it is in this text, especially, namely in the chapter 8, which is called Parahita Ganitam, which we'll come to it later also, we get to see this Uyirēḻuttu in complete action. So this is one verse. I will not bother you with the entire wording of the verse. Just pay attention to the words that are highlighted in red, namely Mannan Veedu Sulkulam, Palliyoni, Yerirma. So these are numeric. They are numbers represented into this Tamil word. So Mannan Veedu Sulkulam stands for the number 15,65,411. Similarly, Palliyoni stands for the number 3,031. And Yerirma stands for the number 248. So these are the numbers which I will explain further. Both myself and my colleague Dr. Pai would explain these in detail. But here it is, I want you to take note of the fact that this Uyirēḻuttu scheme, which is a novel vowel-based scheme, is in action seen in chapter 8 of this text called Cūḍāmaṇi Uḻḷamuḍaiyān. Next, please. Now, this Cūḍāmaṇi Uḻḷamuḍaiyān is in fact one of the prominent Tamil Jyotidam text because it is as gauged from this Union Catalogue of Tamil Manuscript published by the Tamil University in 1991, lists 61 manuscripts of Cūḍāmaṇi Uḻḷamuḍaiyān in different collections. And in this count, only 11 from the Tanjavur Saraswati Mahal Library are included. Next one, please. But when Dr. Satyabhama takes it up for the critical edition, she notes that among the 400 manuscripts that they have pertaining to Tamil Jyotidam, Cūḍāmaṇi Uḻḷamuḍaiyān takes the maximum number of copies. That is, there are 19 copies of it. So this text definitely seems to have attracted a lot of popular and scholarly attention for it to have been made so many copies. And very briefly, if you look at the content of this the chapterization of this text, there are 9 chapters, and from chapter 1 to 7, they deal with basic definitions of astronomical sciences, general guidelines, horoscope analysis, matchmaking, so on and so forth. It is only the chapter 8, which is titled as Parahita Ganitam, concerning motion of sun, moon, and planets, and chapter 9, which concerns eclipses, titled Jayantamale, is exclusively on on astronomical computations and calculations. Next one, please. Now, about the work and the author, the text itself carries this verse, which goes as Madhavar Munbu Sunna Vadamuri Ganitha Nulai, Teedar Tamilinale Cheppinan Isaitennil, Vedamum Angamum Arum, Kalegalum Virumbi Uman, Odi Ulagukku, Ulagaketra Uraipenan Isaitopam. So here it says Madhavar Munbu Sunna Vadamuri Ganitha Nulai. So this comes in the beginning of this text itself. So he is referring to another text, Vadamuri Ganitha Nulai. So going by the content of it, it appears to be the Parahita Ganita by that is only text that is available before. But that is still an open question as to which Sanskrit text this author is referring to. That is still not clear. It is only a conjecture that this would be the Parahita Ganita that was seen before. So the author is saying that he's referring to that, and he's translating that in Tamilinale Cheppanan. So he's translating that in Tamil. So that is what we get to know about at the beginning from the author about this text Cūḍāmaṇi Uڵḷamuḍaiyān. Now in the next text, he says in verse number 8, Tirukkoṭṭiyūr just a second. He says, Tirukkoṭṭiyūr Nambi, சொற்றவனூர் போர் உள்ளமுடை சூடாமடியன் பொற்றொடி வழக்கையினல் it's quite explicitly here. It also the author's name also get to see as Uڵļamudai Kavi. So we get the text name thereby as Cūḍāmaṇi Uڵḷamuḍaiyān. Next. Yeah. And at the end of the last, as seen from Dr. Satyabhama's version of this text Cūḍāmaṇi Uڵḷamuḍaiyān, we get the verse here. விளம்பிய சகர ஆண்டாம் 1100 வடபுகழ்மங்கை மாமுனி அரியவன்சே இளங்குடி மடவார் காமன் இசை திருக்கோட்டி நம்பி உளம்புக கடித நூலை உரைத்தனன் உலகுக்கெல்லாம். So there are various informations enshrined in this verse. விளம்பிய சகர ஆண்டாம் 1100. So here he gives it's like 1100 in the Shakka. விளம்பிய சகர ஆண்டாம். So which translates to 1178 in the current era. So this is the date mentioned in Cūḍāmaṇi Uڵḷamuḍaiyān. And he also says where he flourished at Pandamangai, which is the place that river. Āryabhaṭīya looks like as though it is, although it is not very sure, but then we can conjecture that his father name is Hari. Ilangudi Madavar Kaman is a Tirukkoṭṭiyūr Nambi. Here we get the author's name Tirukkoṭṭiyūr Nambi. Uڵļamuḍa Kaditha Nūlai Uரைத்தனன் உலகுக்கெல்லாம். So that's how this text concludes. Beyond mentioning the date here, inside the text mentions two other numbers. One I already introduced, 15,065,411, which are called khandas. I will come to it a bit later. And one more khanda is given, which is 15,87,006. So they correspond to the year 1185 and 1244 in the current era. Now there is one more important Vakya text in Sanskrit called Vakya Karana. Again, it is from the southern part of the country only. But this Vakya Karana text, which is a more sophisticated version in incorporating the Vakyas, this is dated 1282 to 1316. So here, the 1282 is much later, at least 100 or 50 years, 40 years compared to two dates that we get from the Cūḍāmaṇi Uڵḷamuḍaiyān. And we get to see early reference from this text Cūḍāmaṇi Uڵḷamuḍaiyān. Next one, please. So this is one of the earliest times we calculate the longitude of the moon. So we visit that verse again, which we will see how this verse and the subsequent verse helps us to compute the longitude of the moon. As I said, mentioned before, there are three words, Mannan Veed Sulkulam, Palli Yoni, Erirma, which stands for these three numbers. Next slide, please. That was the 13th slide. This is the 13th verse. This is the 14th verse, where again, I will not bother you with the entire verse here, but please pay attention to the words highlighted in red. That is, Layyatrandral, Ninir Sengal, Seyyapon Kollum. These are again three numerical, they are numbers represented by the Tamil was using the Uyirēḻuttu scheme. So Layyatrandral stands for the number 2229, which in this context is understood as 22 degree 29 minutes. Ninir Sengal is 2,744, which is to be understood as 27 degree 44 minutes. And Sayyapon Kollum is 5 Rashi, 0 degrees and 17 minutes. So let's see how, using the previous one, which gave us the 3 numbers, and this one, not just the numbers, but also talks about certain arithmetic operations that need to be done. I will just briefly describe that in the next slide, please. That is, you start with the number of days elapsed from the beginning of the Kali Yuga till the given day that you are trying to compute. So from that total number of days, you subtract 50,65,411, which was Vannanpedi Surukulam. Now to the resultant, you divide the residue by 3,031, which is Palli Yoni. Now divide the remainder obtained in the previous division by the number 248, which is Erirma. The remainder obtained in this last division gives the serial number of the Vakya among the 248 Pañcāṅgavākyas, which is to be used in the computation. What is Candravākyā in the Sanskrit text? In the Tamil, in this text, Cūḍāmaṇi Uڵḷamuḍaiyān, it is referred to as the Pañcāṅgavākyas. Now, to obtain the longitude of the moon, we come to the second set of the computation that needs to be followed. So, step 1, start with the product of 27 degree 44 minute and the quotient obtained in the division by 248. Then from the above, subtract the product of 22 degree 29 minutes and the quotient obtained in the division by 3031. From the result obtained above, subtract 5 Rashi, 0 degree and 17 minutes. Finally, to the result obtained above, add the longitude given by the Vakya associated with the serial number found earlier. That is the remainder obtained in the division by 248. So this will result in the true longitude of the moon at sunrise on the desired day. My colleague Dr. Pai will explain this once again using a physical example. Next slide, please. So these are the Candravākyas that I'm first 5 Candravākyas that I'm showing here. One thing to be noted here is that the 4 editions of Cūḍāmaṇi Uڵḷamuḍaiyān that I've shown, they do not give the consolidated 248 Candravākyas in a coherent way. There are, given the popularity of this work, there are other works like Vaimīsura Uڵḷamuḍaiyān, which gives the Candravākyas, and various other works as well. So now we have collated 2 such compilation. We have compiled it from 2 such editions, one is Uyirēḻuttu and Prishtajosir. These 2 Candravākyas, where the first Candravākya is Vinnor-Nathan in the Hoisington's edition and Vitto-Nathan in the Prishtajosir's edition. Both of them, despite being different words, it stands for the longitude 12 degree and 3 minutes. If you look at the Candravākya number 5, which is Thaikadal Odar in Hoisington and Vaithavan Koman in Prishtajosir, see how apparently different words they are. So, but we must here understand that both of them are coding for longitudes using the Uyirēḻuttu scheme. So, Thaikadal Odar or Vaithavan Koman would both stand for 2 Rashis, 1 degree and 19 minutes. Next one, please. Now, given the popularity of this work and various editions existing, one must be very careful in looking at the details of it, because these works directly talk about computation. Now, in the Hoisington's edition that I have shown here and underlined with the green, the one word is Erirma, which is 248. In the verse, it is asking us to divide by 248. In the commentary also, it is following suit. It is asking us to divide by 248. But if you look at the Mudaliar's edition of 1861, in the verse, if you understand it using the Uyirēḻuttu scheme, it is asking us to divide by 247, which is wrong. And furthermore, in the commentary, it is asking us to divide by 2,538, which is even further wrong. Next one, please. Similarly, in the Deshikar's edition, it is again asking us to divide by 247 as per the printed verse. And if you look at the commentary, it is A-L-Thagit. So perhaps it is asking us to subtract 7. And the same is followed in the Dr. Satyabhama's edition of 2007, where the verse, the printed verse appears as Yegil, and the commentary also gives Yegil Kagit. So Yegil Maven Rarindadu, so perhaps it is asking us to divide by 7 in the printed version of the verse in Dr. Kameshwari's edition, and the commentary is going in a different way. So since these are astronomical computation, there is the immediate need of the hour is for Tamil scholars who have penchants for the scientific tradition of our country, and particularly the scientific tradition of Tamil Nadu. It's the need of the hour is for them to come together and have a relook at these verses and their commentaries, and perhaps come out with a blemishless edition of both the verses as well as the commentaries of the same. One more point here, you see that the commentary given in the Desikar as well as the Dr. Kameshwaran's edition, they explain this word Mannan Veedu Kulam என்று 15,60,400 like it, they explain it in Tamil, which is not seen in the case of Paisington or the Mudaliar's edition, which was seen in the previous slide. So with this, yeah, next slide. Yeah, you can open the PDF file. And with that, I conclude, and I request my colleague, Dr. Pai, to take over and show the examples of the computation that we just talked about.
Gauri, you can go in the view, you go to view, you can do full screen. Dr. Pai, you can unmute and continue.
Yeah, unmuted. Yeah.
Okay, fine. Wonderful.
Namaste and Vanakkam. So I'll be explaining a computation pertaining to true longitude of the moon with an example. So the example chosen is 28 February 2025. So our aim is to find true longitude of the moon for 28 February 2025 based on the algorithm given in Cūḍāmaṇi Uḻḷamuḍaiyān. So now for this, we need to know certain technical terms. First thing is Ahargana. Ahargana corresponds to 28 February 2025, which corresponds to Indian calendrical date Magha Amavasya Shaka 1947. So Ahargana is nothing but the group of civil days between desired day and epoch. Epoch is a day when where we have the knowledge of the longitudes of all the planets. Usually in Siddhantic astronomy, the epoch is considered as the Kali beginning, that is February 18, 3102 BCE. So now when I say Ahargana, it is the number of civil days between desired day and epoch, and desired day for us is February 28, 2025. So another parameter that we need to know is Khanda. So that has been explained by Ramanathan. Khanda essentially means a part of Ahargana. And the speciality of that Khanda is nothing but it's a recent chosen epoch where moon's anomaly is 0. When I say moon's anomaly is the longitude of anomaly of the moon is 0. So here you can see a diagram where you can see a circle with the center of the circle is Earth, and the moon is revolving around the Earth. And you can also see a vertical line which is marked as U, which is moon's apogee. So as we know that all planets are moving in a non-uniform motion, apogee is nothing but the point where moon's motion is least. Moon has the slowest motion. So now we need this happens. So when this apogee is also actually moving, moon is also moving. Apogee is moving in a very slow rate of the rate of motion of the apogee is very slow. So it's as Professor Ramanathan has pointed out that it's about 27.55 civil days. It's an average period of the anomalistic revolution. So at every 27.55 days, moon will coincide with its apogee, which means the longitude of the moon will be same as the longitude of the apogee. So that their difference in longitude would be 0 on that particular day. So we need to choose khanda in such a way that the longitude of anomaly should be 0 at the time of sunrise. And the value of khanda is given in all of the Vakya texts. That is, the Vakyakarana gives one khanda which is close to the composition of Vakyakarana. Cūḍāmaṇi Uḻḷamuḍaiyān gives another khanda which is Mannan Veedu Sulkulam. So next slide, please. Next slide. Next slide, please. Yeah. So the khanda given in Cūḍāmaṇi Uḻḷamuḍaiyān is Mannan Veedu Sulkulam. That corresponds to 15,65,411. And the Ahargana corresponds to February 28, 2025 is 18,72,269. So what one has to do is we have to find the difference between Ahargana and this khanda, that is A minus A dash. That is 3,06,852. That is the first step we need to do. And then finding khanda shesha, which is the difference between khanda and Ahargana, we need to divide this khanda shesha by 3031. Next slide. 3031 is again the period of anomaly. That is anomaly. This moon's conjunction with apogee happens 112 times in 3031 days. So 112 by 3031 is the number of anomalistic revolutions or the conjunction of moon and its apogee and 3031 is the number of civil days in which these 112 conjunctions happen. Similarly, 248 is another number of civil days where 9 anomalistic revolutions of moon. So these are the astronomical significance of these two numbers, that's 3031 and 248. So first we need to divide 3,06,852, which we got from subtracting khanda from Ahargana by 3031. We'll get quotient as 101. And the remainder we get is 727. So the first, let's call it as Q1 and R1. That's first quotient and second, first remainder. Now, so there is a small typographical mistake here. So it's actually 727. Second quotient can be found by dividing 727, that is the first remainder R1, by 248. And the quotient we obtain is 2, that is the second quotient. Similarly, 727, when we divide it by 248, and the remainder what we get is 231. Next slide, please. Similarly, all these texts, Vakya texts, including Cūḍāmaṇi Uḻḷamuḍaiyān, gives something known as dhruvas. Dhruvas are nothing but the true longitude of the moon. At the end of this khanda, which means the true longitude of the moon on the day of khanda, 15 lakhs and so on. That is Mannan Veedu Sulkulam. That is given as Shayya Pongullum. Shayya Pongullum is the dhruva given by the Cūḍāmaṇi Uḻḷamuḍaiyān for the khanda Mannan Veedu Sulkulam. That is 15,65,411. That means on this day, the moon's longitude would be minus 5 Rashi, 0 degrees, 17 minutes, which is nothing but 360 minus that particular longitude, which will give us 6 Rashis, 29 degrees, 43 minutes, which when we convert into degrees, we have 209.717 degrees. Similarly, there are other dhruvas corresponding to 3031 and 248 are given, which means suppose today's moon's longitude is suppose 0. After 3031 days, the moon's longitude will be minus 22 degrees, 29 minutes, which is given by the phrase Āryabhaṭīya, that is minus 22 degrees, 29 minutes, which is nothing but plus 11 Rashis, 7 degrees and 31 minutes, which can be converted into degrees as 337.517 degrees. Similarly, for 248 days, which means suppose today is the moon, if today if the moon's longitude is 0 degrees, then after 248 days, it would be 0 Rashi is 27 degrees and 44 minutes, which corresponds to 27.733 degrees, which is given by the phrase Ninir Shengal. That is the phrase given in Cūḍāmaṇi Uḻḷamuḍaiyān. So now, how do we use these dhruvas and the quotients? We have to multiply the quotients obtained by the corresponding dhruva. That means Q1 is the first quotient that we have obtained. Q2 is the second quotient that we have obtained. So D1 has to be multiplied by Q1 and D2 has to be multiplied by Q2. And their sum has to be added to the dhruva 209.717, which is nothing but D0. Dhruva at the end of khanda. So that will give us D net, that is the net value of the dhruva. Now already we had next slide please. We had remainder. When we divide Q1 by 248, we got quotient as 2 and remainder as 231, that is R2. That gives the serial number of the Vakya. So that serial number of the Vakya will give us the true longitude corresponds to that day from first day. That is, the first day was Vittornathan in Tamil Candravākyas. It was the first Vakya was Vittornathan. In Vararuchi's Candravākyas, it is Girna Shreyaha. So now, next slide, please. This D net has to be added to this Vakya Tata Vonalgum. That corresponds to 5 Rashis, 10 degrees and 22 minutes. So this 5 Rashis, 10 degrees, 22 minutes corresponds to 160.367 degrees, which has to be added to 1554.400 degrees, which we got earlier. This would be the final true longitude of the moon on 28th February 2025, which corresponds to 314.767 degrees. So when we compare this with the observational data, which is from ephemeris, the true longitude for that day is 314.999 degrees, which is around 0.2 degree error. Which the computed value using the algorithm given in Cūḍāmaṇi Uḻḷamuḍaiyān and based on the parameters given in Cūḍāmaṇi Uḻḷamuḍaiyān, it's the result is fairly accurate when we compare it with the ephemeris value. So, yeah, thank you so much.
So, thank you, Dr. Pai and Dr. Ramanathan. I'm very grateful to the Tamil Heritage Trust for this organizing this talk. In this concluding portion, I just want to summarize the astronomical significance of the text Cūḍāmaṇi Uḻḷamuḍaiyān to the extent we have looked into it. You see, in ancient Indian astronomy, we have both the Siddhantic and Vakya Pañcāṅgavākyas, but actually the basic system is the Siddhantic system. And the Vakya system is only a simpler way of computing approximately the values that the Siddhantic system gives. So it is not a different theoretical framework. It's a computational framework, mostly relying upon arithmetical computations. So in Siddhantic system, we first compute the mean longitude, at least from the period of Āryabhaṭīya of 499 or Pancha-Siddhantika of Varamihira, which describes various Siddhantas as they were in the earlier couple of centuries. So we first compute mean longitudes, then we do various corrections, which depend more on geometrical pictures, on sine tables, trigonometric functions, arcs and chords, and things like that. The Vakya system instead goes with more simpler computations from true longitudes to true longitudes, using various intermediate points called khandas, various periodicities of the celestial bodies, their abscess, nodes, etc. Next one. So the basic anomalistic cycle of the moon has been talked about. Moon, with respect seen from the Earth, makes a complete revolution amongst the stars in 27.32 days. The apogee, or the farthest point of the moon from the Earth, where the moon's velocity is slow, that is also moving, and it moves in actually 3,232 days or 8.85 years. So moon and the apogee catch up with each other in 27.55 days. The motion of moon roughly goes around 13 degrees 20 seconds per day with respect to the stars, but its daily motion is not uniform. Instantaneous motion is also not the same. The first approximation to that depends upon the difference in longitude between the moon and the apogee. And so this anomalistic period where moon and apogee come back to each other is a good way to make a table of true longitudes of moon. So these 9 anomalistic months are about 248 days, 110 anomalistic months are 3,031 days, and 449 anomalistic months are 12,372 days. Next one, please. So the Candravākyas can be computed from the Siddhantic astronomy. Use the mean value of rate of motion as 13 degrees, 10 minutes, 35 seconds. And use only the simplest correction called the equation of center or the Manda correction in Indian astronomy. Then the true longitude is given by this equation. Theta is theta naught minus sine inverse of 7 by 80 times sine of theta naught minus theta. Theta naught is the mean longitude moving at the rate of 13.1764 degrees per day. So 7 by 80 is the relation to the eccentricity of the moon's orbit. Theta c is the Chandrocha, the apogee of the moon. So now we know that in 248 days, moon and the apogee together make 9 revolutions. So the rate of anomalistic motion, the rate of variation of theta naught minus theta c is 360 degrees divided by 248 by 9. So you can calculate for each day how much the true longitude changes. This is called the method of computation of the mth Vakya for the mth day. So in a cycle of 248 days, you can compute this. Cūḍāmaṇi Uḻḷamuḍaiyān, to start with, has 4 verses which discusses the method of computing the Candravākyas and also the method of checking. And again, amongst the works available to us today, this seems to be the earliest work. Next one. So the Vakya system is an ancient system. This 248 days and 9 anomalistic months. This period was known to the Babylonians also. But they were computing, they were tabulating daily results, and they were using computations of uniform motion for each day, such that moon and the apogee come together in 248 days. So that is like approximating the sine function by a zigzag. They were doing it in tables. In Varahamira's Vasishta Siddhanta, that portion of Pancha Siddhantika, there is a description of that which uses both 248 and 3031 days. There is an analytical formula for calculating the daily velocity of the moon and the longitude of the moon. This Vararuchi's Vakyas, which are computed on the basis of true sine function, not in the Vasishta Siddhanta format, are attributed to 5th century, and those 248 Vakyas were attributed to him. Another development was this Parahita Ganita of Haridatta in 683. That does not contain any Vakya method of computation. It's a simplified version of the Āryabhaṭīya astronomy or Āryabhaṭīya and Bhaskara I's astronomy using kaṭapayādi and simpler calculations rather than the complete Siddhantic calculation. So the simpler calculations are generally called Karanas or manuals in Indian astronomy. So the Vakya system seems to have developed after the Parahita system, but when it happened, we have Vararuchi is attributed to 5th century on the basis of other literary evidences in Malayalam literature. We don't know exactly. There is also the Vararuchi who wrote the Vartika to Panini's this thing, Katyayana, who wrote the Vartika. The first detailed treatment of the Vakya system appears in the 13th century, end of 13th century, in a Sanskrit text called Vakya Karana. Author is not known. It was composed in Kanchipuram. Again, in Kanchipuram, an astronomer called Sundara Raja wrote a commentary on that. So this is the first, till recently, this was the only known first available text on Vakya. Then there is a huge literature on Vakyas, both in Kerala and in Tamil Nadu. Next one, please. So the Vakyakarana method, they have already explained that the Vakya method. So you start with the Hargana for the day, subtract the Khanda. The Khanda gives the date on which moon and the apogee are coinciding, have the same longitude at sunrise. Then use these anomalistic periods, 12,372, 3,031, 248. So Vakyakarana uses 3 of them. Cūḍāmaṇi Uḻḷamuḍaiyān uses 2 of them, 248 and 3031. So for each of these anomalistic periods, we know how much the true longitude of the moon changes. So there's an arithmetical multiplication and subtraction involved. And finally, for the starting Khanda, so Vakyakarana, it is 16,984 days was the starting Khanda, which corresponds to 1282 of the common era. So you have to add a dhruva corresponding to that. So this is the method which both Pai and Ramanathan have explained. Now let's go to the next slide, which summarizes the way the Cūḍāmaṇi Uḻḷamuḍaiyān has tackled this and the way Vakyakarana, which is perhaps 50-60 years later. Both are coming from Tamil Nadu. Cūḍāmaṇi Uḻḷamuḍaiyān is in Tamil and Vakyakarana is in Sanskrit. Cūḍāmaṇi Uḻḷamuḍaiyān says that this is discussing methods which are known in earlier Sanskrit texts, which we do not know. It's not the Parahita Ganita of Āryabhaṭīya. It's a later text which we do not have. So you can see the Khanda of Cūḍāmaṇi Uḻḷamuḍaiyān is 15,65,411. That of Vakyakarana is 16,984. The corresponding amount that needs to be, in the case of Cūḍāmaṇi Uḻḷamuḍaiyān, it's subtractive. You subtract 5 rashis, 0 degrees, 17 minutes. Shayyapon Kollu. In the Vakyakarana, it is given by the kaṭapayādi, Sena Nari Nathanaha, 7 rashis, 2 degrees, 0 minutes, 7. And these divisors, Vakyakarana has extra divisor, 12,372, Rasa Gairika, and corresponding dhruva corresponding to the Nitya Deva Sukhadina. And there are 2 divisors which are common to both Cūḍāmaṇi Uḻḷamuḍaiyān and Vakyakarana. This Palliyoni or Kalanala, which is 3011, and Erirma or Devara, which is 248. And the Cūḍāmaṇi Uḻḷamuḍaiyān dhruvas are only up to the level of minutes, and the Vakyakarana dhruvas are up to the level of seconds. So it is more accurate. Vakyakarana also has a further correction because in 248 days, moon and the apogee are not exactly coincident as we saw in the first slide. So there has to be some correction. Similarly for 3031 days. So Cūḍāmaṇi Uḻḷamuḍaiyān is genuinely a simpler version of Vakyakarana which comes later. Cūḍāmaṇi Uḻḷamuḍaiyān does not have the planetary Vakya computations which are there in Vakyakarana also. Now just to some historical thing in the next 2-3 minutes, an important fact that in 18th century, Lejeantel, when he came to see the transit of Mercury in Pondicherry, he got this Tamil Vakyas computations done. And here is Nagyabhad explaining that there seems to have been some rivalry between Hindu Brahmins and the native Tamil population. The Brahmins trying to conceal the existence of a Tamil tradition of astronomy besides their own. Nevertheless, Lejeantel eventually succeeded to get somebody who was well versed in the astronomical methods of his people. So Nagyabhad in 1948 started talking about Tamil tradition, and he traces it to the Babylonian 248 and some Greek papyri in 1st and 2nd century AD, which used the 3031. And of course, he remarks that the Tamil method gave a very accurate value for the eclipse. Next one, please. So Nagyabhad also quotes the statement of Lejeantel, who says that the Tamilian method is very simple and very see whether that can be used. So he tries to make a joke out of it. Nagyabhad also talks about another case 50 years later. Colonel John Warren was the chief of the Madras Observatory. He went to Pondicherry and got a calculation done by Swaminathan Sheshaya, another astronomer there. And he also found the eclipse calculation very good. Next one, please. So this Lejeantel's, John Warren's book, Kala Sankalita, is published in English. So all of you can read it. It's available on archive.org, 1825. Lejeantel's book is in French. About 2 years ago, it was translated by Anil Narayanan. So he is trying to explain what Lejeantel actually said, though as I will show, he has only said it partially. So this is what Lejeantel says, that when I came to India in 1768, I knew from France itself that Indian astronomers were very good in earlier reports from Jesuits had told him they were very good in calculating eclipses. And so he contacts this ஞானமுத்து, who comes the next day. He tells him, why don't you come tomorrow and calculate the eclipse of December 1768? He comes the next day and he calculates the entire eclipse, all the parameters of the eclipse in just 3/4 of an hour. Then Lejeantil tries to, of course, checks it with the Mayer's tables, which was the most advanced ones, and the values are similar. And then he gives him other eclipses to calculate. Each of them he calculates in the same facility and the same fastness. And then Lejeantil says they perform, this is the statement which Āryabhaṭīya has quoted in French. They perform their astronomical calculations with singular speed and ease, without pen or pencil. They replace writing with cowries, a sort of shells, which they place on the table like our tokens, and most often on the ground. The method of calculating seems to have its advantages in that it is more prompt and more expeditious than ours. It is after this line that Āryabhaṭīya says, imagine the members of French Academy trying to work with shells on the floor. And then he says, there's one problem with this calculation, that they erase the whole thing at each point. So if there's an error in the calculation, you have to do it once again. But of course, they could do the whole calculation in 45 minutes, so they could do it. So he says the Indian astronomers work with a singular coolness, a calmness and tranquility of which we are incapable, which enables them to avoid the mistakes which we make. So anyway, this method is not good enough for ourselves. This is what Lejeantil actually says. We cannot avoid mistakes. Next one, please. And finally, Lejeantil, how he explains, actually Lejeantil is explaining the Vakyakarana method, not the Cūḍāmaṇi Uḻḷamuḍaiyān method. So he is referring to Vedam, Rasam, Kalam, Devaram. That is Vedodha Jnanatushta. That is the period 16 lakhs, 3094. Revised at 12,372. Kala Anila is 3031. Devara, which is 248. And then the corresponding dhruvas he is giving. And all this is he is explaining. Now, the fantastic thing is you go back to Lejeantil's book. Now, the way Anil Narayanan has translated, he has kept on saying Indian method, Indian period, Indian period. I just show you the last slide, how Lejeantil is writing about the whole thing. Next slide, please. I see, there is one more slide. It's not there, is it? Okay. Lejeantil is referring to the Brahmins' astronomy, their way of calculating eclipses. He is calling these numbers as the Brahmins' numbers, periods for the computation of moon. It's in the page 273 of Lejeantil's memoir published in Paris in 1779. So there's complete mess up of all this, which is true that 18th century Indians were as good in computing eclipses, but this Vakya method does not work for everything else because it's accurate only when the longitude difference between the moon and the apogee, moon and the sun, is 180 degrees or 0 degrees. So it is good for Amavasya and Purnima. For other periods, it misses a correction called evection, which was used in Siddhantic astronomy in India from about 932 onwards by Munjala. I think I've explained sufficiently about the importance of how from the older calculations, the Vakya method evolved into a very simple calculation, and much of it developed in Kerala and Tamil Nadu. And both the Tamil text and the Sanskrit text in Tamil Nadu have contributed immensely. We have studied the Sanskrit text quite a bit of both the Kerala and Tamil Nadu. We should study the Tamil text, and that they are very important for understanding the development of this and the popularity of astronomy amongst people in India, the accuracy and the felicity with which they calculate. Thank you very much.
Sir, is there any part of the lecture that is still pending, or
No,
we can
sir, no,
go to
no. We can have any discussion.
Can we have others also come up on
Yeah.
video?
While you also come on the video.
Yeah, I will add everyone. Second. Great. Sir, let me start by saying that it is a relatively difficult topic for most of us. There are there are 3 or 4 different planes at, which we need to understand. The first is the astronomy itself, because you're using quite a few astronomical calculations, ideas, words, etc. And then the, I'm talking about a lay reader, the Sanskritic alphabetical numerary system. And then you want to compare that with the Tamil system, the Tamil numerary system. So it's too much in a sense of absorbing it. You are all experts in the field. So for you, it is relatively easier. I see that there are very few questions because people probably didn't even know what to ask. But I do have some questions. And there is one important question that we really need to address. So a question from Rajesh Garga. He says, how does one figure out which part of the verse? And he's specifically talking about the Cūḍāmaṇi Uڵḷamuḍaiyān, the Tamil text. And I assume that it is the same thing that is applicable to the kaṭapayādi system also.
Yes.
But before that, let me repeat this question. How does one figure out which part of the verse is textual and which part is used to denote numbers? For example, Seyya Ponkollum is considered as number, but not andre. Right? That just, if you take that example.
A very good thing. So people, this is a 50 verse chapter giving the entire Parahita astronomy, motion of sun and moon. This chapter which we are discussing. This is the 13th verse giving the Vakya method for computing the moon. So there is a commentary on it. There is a Urai. So it's the Urai which will put the phrase which needs to be this thing in Parahita. But the Urais in both the books are more or less, all the editions are more or less the same, except for the errors which are widespread. The different errors are made in different editions. But the Urai or the commentary clearly picks up. And in fact, one commentary even mentioned for the 15,65,641 is the number that is given by Mannan, Vidishul, Kulam, etc. So otherwise, so even in Sanskrit, in that Bhaskara's verse, Rasaguna Mahi, Rasaguna Varshe Mama Janmaha. So you have to just immediately see that he's talking of a number there from the context. Right? So Āryabhaṭīya will Harit. So divide by Āryabhaṭīya, divide by 248. Palli on Hil Harit. So the verse will more or less make it clear, but still the commentary is needed.
So if we remove the commentary, it would be difficult for us to figure out which are...
No, only astronomers will read it. They know already 248, 3031, etc. from other contexts. Or if it is the first time they are reading it, they have to read it with comment. Okay. If a Sanskrit astronomer who knew Tamil read this, he would have immediately understood what is going on of that period.
Okay. So the question that I personally have, I wouldn't, again, I don't claim to be an expert in any of this, but to me, looking at the text, and I'm reading the text only now with whatever you have quoted of Cūḍāmaṇi Uڵḷamuḍaiyān, I see that there are sort of, again, maybe I require a lot more of reading and coming back. There seems to be sort of 2 different layers. I'm not talking about the commentary. I'm talking about only the verses, and they are in 2 different meters. And the ancientness, we are talking about 12th, 13th century, and you have an internal reference. Somehow it feels to me, having been reading Tamil literary text from the Sangam era to to the 19th, 20th century, this doesn't seem to have the 12th to 13th century ring to it. This is my very humble submission. I am not...
No, sure. No. You see, this has 4 editions it has gone through. The astronomy part, nobody had cared to see. So now our Ramanathan and Pai have come forward to look at it and sort of decode what is the astronomy part. I'm sure there is too many sociological, historical, linguistic, and all information contained in Pandamangalam. There is also the Tirukkoṭṭiyūr Nambi, so many things. You see, the Surya Deva Yajvan is more or less born at the same time. He's a very great astronomer in Gangakonda Cholapuram.
Right.
This Vakyakarana is being written in Kanchipuram in 1282. And so this is a very flourishing period of development of astronomy. We are trying to look at that. But this contains a lot of historical. In fact, Ramanathan had called attention to a verse in an earlier chapter about the age in which women should start their education. And this being written in a 12th century text, remarkable kind of thing. So various sociological, historical, and various things are there. Linguistic things are there. Philological analysis is there. So because of the difficulty of understanding of the text, because one needs to know astronomy, the editions are defective. Otherwise, Satyabhama Kameshwaran has edited about half a dozen important Tamil mathematical works. It's very silly to see her missing Eri, Irma, Yedi, Kaliti, and all that. They made a mishmash of the whole thing. Whereas Subbaraya Muraliya, like 1861, perhaps still was an astronomer. So his edition is more or less all right, but for a very small this thing. So we have lost this tradition. So we have to acquire both scholarship in Tamil tradition of astronomy and also in Tamil scholarship to read these works. You may be right, it may be 14th century, but he is saying 1100. There are two khandas which appear in this book. One which is 15,65,411. Another is some 15,85,000. They correspond to 1185 and 1244. Now, Vakyakarana is a well-known Sanskrit word. Its manuscripts are there both in Tamil Nadu, Kerala, Andhra, everywhere. That is dated at 1282. But this is a more preliminary version of that. It is mostly Parahita and some Vakya is there, and especially of the moon. So it's somewhere in between. So even if this edition or the sort of even the corresponding verses quoted are somewhat of a later thing, there would have been something written at that time, which is sort of in between Vakyakarana and the Parahita. This is my submission, speculation, because I have no. Ramanathan, you want to say something more?
Yes, sir. I agree. I mean, I nothing more to add. But then what Dr. Badri also has raised is that the Chandas is not kind of appearing of that age. But as you rightly said, more of Tamil scholarship has to be invested in this. Even if we give discount to that internal evidence of 1100 Shaka era, the two khandas that are coming there, well, the Mananvid Surkulam, the what is it, 65,411. Those things are irrefutable. That is 1185 and 1244, the date comes out. So, notwithstanding the Chandas mismatch of that era, these two numbers we cannot ignore. Even if
they give good values in computation for eclipses and.
That's why I'm being very, very careful here. But one thing I should certainly say that for us, sorry, some other echo happened. So one thing I would say is that we, in a general literary kind of a background, had never heard of this numerary system until now. Until you started talking about it in Twitter here, there, and then we started talking to you about a lecture, and then you wanted to have the paper published. This is a completely new thing in the the public space. I don't know if Tamil scholars or mathematical scholars knew of an existence of this numerary system.
There is a book of 1895 due to Krishna Joyishya called Pañcāṅgavākyas.
Okay.
That has explained this numeration system. But that we saw after we decoded the astronomy of this.
I see.
Pañcāṅgavākyas, Jyotir Ganitam in Tamil, a 250-page book on Vakya system and other aspects of astronomy. But Munam Panni Krishna Joshi, he was a famous astronomer in last century, 1895. It has been republished in 1935, also available on archive.org. The thing is, all these books are available, but nobody is reading.
Nobody has studied it. I understand. I think people pick up Saraswati Mahal content and then scan it and put it in archive.org. But there is no critical study by a subject scholar who also has an understanding of the linguistic aspect of it.
Yes, absolutely.
So the other thing it opens up is how kaṭapayādi allowed you to create, see, the only numerical system which is sort of coming up with non-words is Āryabhaṭas. Complete
Compression. It's just basically compression.
It's just some made up word, but both the bhūta-saṅkhyā and the kaṭapayādi allowed a clever poet to code the right word so that you could actually read through a very interesting looking text. Now this Tamil numerary system allows the same degree of encoding. Same degree of encoding, that it is surprising that
a higher degree of encoding actually, because it uses only vowels. If you see, it actually allows more flexibility in terms of what words you can form than even the others.
I think we can say both systems allow creation, because there the vowels don't have value, and you can have any vowel there because that's a consonant. Here you can put any consonant on top. There you can put any vowel on top.
Absolutely different sounding words still were leading to the same number as if you would like.
No, it doesn't matter. The same thing is available there also. Okay. So the way to really look at it is that how is it that poets who also wanted to give coded message did not make use of this, or have they used it and we don't know? So if it is known, like the Krishna Josier talking about it, from the time of from post, let's say, Kambar in his Kambaramayanam, and subsequently, because we are sort of talking about the prevalence of this around that time.
Yes.
Take Surideva Ejwan to Tirukkoṭṭiyūr Nambi to Kambar, they are sort of roughly roughly thereabouts, mostly living in and around the Chola kingdom or the periphery of the Chola kingdom in Kanchipuram or wherever it is, that I am surprised that it is not found mentioned anywhere else. So that requires a wider combing of the text to just see if this system was used for something else or the other.
Yes. There are many inscriptions which use that numerals, Tamil numerals in the 12th, 13th century, 14th century, as Ramanathan pointed out. We have not come across inscription, but very few of them are published fully. So inscriptions are a bigger corpus. But there is a V Uڵḷamuḍaiyān written in 17th century, which uses the same numerical system. It's also published. There are 400 manuscripts on Jyotishan in Saraswati Mahal. Maybe there are 200 in Oriental Manuscripts Library, but not many of them. But there are some manuscripts on Sputagaritam, Pañcāṅgavākyam, things like that. One can start looking at them and there. But this Candravākyas, apart from that, the whole of planetary Vakyas and other Vakyas, the Hoisington's book of 1848 has all those Tamil Vakyas. It has printed all of them. Because its main idea was that the missionary should know the local system of astronomy for them to be able to communicate. So the Batikota seminary made it a point, and he translated it into English also, somewhat faulty at various places, but it is still serious work.
If I may go a little bit away, your last few slides, Dr. Srinivas, your last slide,
yes,
I see that there is scope for some controversy. In a politically charged Tamil Nadu with the Brahmin, non-Brahmin controversy. Maybe you can, we are an academic forum at this particular point, so ignoring what other way in which this would be seen, you see that, is it Nugbor who's suggesting that the Brahmins were sort of hiding or sort of keeping away the Tamil system, which by definition is not by Brahmins? Is that sort of
what? He is suggesting that No. You see, the problem is that Western Indologists read very few of the Indian texts fully. But whatever they read quite carefully. So, and they think if they read one text, they know everything. And so there's a great problem. So Āryabhaṭīya is one of the most eminent historians of the first half of 20th century. And David Pingree, the major American Indologist, who was historian of Indian astronomy also, was its he was mentored by Āryabhaṭīya. He was David Ingall's student, but he was mentored by Āryabhaṭīya. So Āryabhaṭīya wrote a paper in 1948 called Tamil Astronomy. And there he said this Tamil astronomy is using Babylonian methods, and it is not using Siddhantic methods at all. It's a very different tradition. And then he said the periplus of Erythraean Sea and all that. Tamil Nadu had very Arikamed, which is so close to Pondicherry.
Right.
He had read John Warren's book Kala-Sankalita then, when he wrote that paper. And in the end footnote, he says, I know I've been told that there is a memoir by Lishantil also, who came to Pondicherry in 1769 to see the transit of Venus. So there he only makes a passing reference to Lishantil. Now, I don't think he has read Lishantil, so he's making a quotation partially and then misrepresenting, saying he had great difficulty and they did not. There is no such thing in Lishantil, at least in the translation of Anil Narayanan. But Anil Narayanan, wherever Brahme occurs, he is not saying Brahmins, he is writing Indians. So it is some new idea of political correctness that he is doing. Now, all that is said is that in 18th century, people here knew the Vakya Karana method. There is nothing secret because that's a Tamil method discovered in Kanchipuram in 1282. There is perhaps several Tamil texts which will be discussing that also. Cūḍāmaṇi Uḻḷamuḍaiyān is an earlier version of that Vakya method. They made this Tamil astronomy. No, just last one small point.
No, go ahead.
1960s, I think 67 or something, Professor Subramaniam Chandrasekhar, who got Nobel Prize later, nephew of Raman, was invited to give a talk, Jawaharlal Nehru Memorial talk in Delhi. So he talked about the history of astronomy in general. He said, but I will tell you something about Indian astronomy. I have learned from Āryabhaṭīya that India had two traditions, the Sanskritic tradition and the Tamil tradition. And the Tamil tradition was separate and it was arithmetical. It linked to the Babylonian tradition, and the Sanskrit tradition was geometrical and it linked to the Greek tradition. So he more or less repeated verbatim what he had learned from such a great scholar of history of astronomy and astrophysics. So this is a problem. So once an idea is floated, I am seeing a paper in 2023 written by a Swedish scholar saying that the Tamil method of calculating the parallax. So what he does, he goes back to Lishantil's book, and there is a description of what is called parallax, which is to be calculated in an eclipse. And he is discussing that. Now, there are so many explanations of Vakya Karana, which are all discussing this parallax. Commentary of Vakya Karana by Sundar Raja is there. They all don't want to look at it because they have only seen Āryabhaṭīya and then now writing Tamil astronomy and parallax. And even Anil Narayanan, who publishes this book in 2022, there is no reference of Vakya Karana. He also thinks these numbers 248, 3031 are mysterious, except that they were known to the Greeks and the Babylonians. So I think we have what is called problem of poor scholarship following eminent Western Indologists. So we have to do serious scholarship.
Okay. No, I think, you are, at one end, you are opening up an interesting area for a lot of scholars to study, but we'll also have a lot of trolls on YouTube.
Yes.
You have given million videos that YouTube trolls can come up with. So I will refrain from that. Just a couple of points on the even when you look at, if you are analyzing the names, right? Why is it that you call it as, the Westerners who looked at it, they were calling anything written in Sanskrit as a sort of Brahmanical text, and the Tamil one as Tamil text, because Tirukkoṭṭiyūr Nambi is a very obvious Vaishnavite name. There is no two ways about it. Sundar Raja, these are all names which have very, very clear connection even the one who wrote Kutakara Shiromani, it's very, very clear what kind of background they have.
Devaraja.
To really introduce these kind of divisive names unnecessarily causes needless 21st century sociological mess.
The person who informed Lijantil was Jnanamuttu. And I don't know whether you can immediately make out his community from
most likely a Christian is my first reading. When the name Jnanamuttu came there, it's most likely a Christian.
Could be, but Lijantil says he had an interpreter with him who was a Christian. But the other person he brought, he says Indian in Anil's translation. Now I have to check up Lijantil to see what is.
I am now, names like Jnanamuttu is a very, very closely associated with the Christian name. It's what my first reading.
John Warren, whom he met, that person is called Saminathan Sheshaya. Now there are various, this was done in Siam, they got similar tables, which are similar to what are called Tiruvarur tables here in early 1700. So the French ambassador is transmitting them. So there are a whole lot of discussions of French Jesuits and various tables also. So they have been discussed in France by Cassini, and this Lijantil is the assistant of Cassini. So there is quite some literature. One can do some sociological analysis of that also and historical analysis of that also.
I think good reading and extraction of the math and science part of it is very important, but also look at other layers as you indicate. In a serious sense would help us. Certainly it's a fascinating new area from those of us from the non-scholarly world, if I may say. And I can see that there is a lot more that we have to first of all understand and take to public about a Pañcāṅga text with the calculation, particularly as Dr. Pai was showing a lot of calculation. It was a little difficult for us to follow because we have not seen that. So there is, I think, a scope for a simpler explanation of, this is what the text says, and this is what it means, and this is how you calculate. And what would be interesting is, therefore, give people the text to say, can you find the the position of moon today? If this text is now accessible to you, and I teach the various Candravākyas to you, to school child, I think it could be a very nice way of introducing it.
Just a point. 80 years ago, when the first edition of the Sanskrit Candravākyas was published by a scholar called Punhan Raja from Adyar Library. So he wrote in the preface that as children, which would have been 50 years earlier, they were all taught this. These 248 Vakyas were taught in their childhood. And then they were using whatever Khanda and making, because these are arithmetical. People can use. In fact, the Kerala, the word for, I think, kaṭapayādi itself is the shell number or something like that. Paralpera. Shell name. So the shells were showing the position. So this was taught to everybody. It's not very accurate, as I said, outside of Purnima and Amavasya. Not very accurate. It's that half a degree, 1 degree, 2 degrees. Moon moves 13 degrees in a day. So at sunrise, you may have an error of 1 degree or something like that. So Pai was fortunate to get the 0.2 degrees for his Magha Amavasya. But it can be improved. This Vakya can also be improved. If the scholars look at it, there may be. There are good scholars like Professor Sriram and various, they can improve this by taking into account sun's position also. There is some improvement.
And if you improve, you might as well come up with a new Uڵļamuḍaiyān text, because you just have to recompose the appropriate words for a more accurate thing. And it can be then memorized for fun. So that's what I was indicating.
Absolutely.
Instead of, if there are errors, the errors can be corrected. and new Tamil words created so that it can be memorized and you can teach just for fun. I mean, today with ChatGPT will probably tell you everything that you need to know, but there is no fun in it.
Not only that, there is some astronomical understanding you derive. Everybody has become wiser.
Exactly.
Yeah.
From ChatGPT, you don't become wiser. You only get some answer.
Correct. That's correct. That's correct.
So,
Correct. Yeah. So wonderful, sir. I think there's
Why you won't say something, sir?
Yeah.
No.
So Ramanathan, would you like to add anything? Otherwise, we can sort of wrap up.
Just one line. Basically, I got picked when you said this last question. My calculation seemed a little bit intimidating. And what Professor Srinivas also narrated, as a one line, what I feel as a Tamilian also now is that Tamil, despite having a very intellectual past, both in Sanskrit as well as in Tamil, but somehow now the Srinivas made a very beautiful sentence that of course scholarship is just following Western knowledge. And as said, intellectual pursuit itself is quite.
Your audio is getting chopped.
Now you tell.
Is it better now?
Yeah,
absolutely.
Yeah. What Uyir was saying that getting the in that getting human birth is rare. Intellectual pursuit itself is rare among the lay, and in that a subject like Tamil, like there a subject like astronomy is even more rarer. To know that our Indians in the past had the penchant for such a complicated subject and simplified it through various means indicates a lot of degeneration in the education system. Much to do about to bring them back in the mainstream, leaving aside all the political controversies, and then bring the mainstream back. As Professor Srinivas mentioned 80 years back, these were taught by heart. The bhūta-saṅkhyā like Urukulam, that bhūta-saṅkhyā that I showed in Tamil. It is there perhaps in all the state languages. They were taught by heart in the school. That all gone now.
Right.
So we need more scholarship in the mainstream, and with such efforts, maybe we should be able to do some bit towards that direction.
Wonderful. Thank you. It's going to be 7:30, and
yes, sir.
Thank you.
Very kind of you to have organized this stuff. Thank you very much.
We are really grateful to all three of you to have spent the time and presented all together different aspects of this particular relatively complicated one for the because of the background. It is not I think amongst the scholars you probably have much better understanding, and really we are thankful to you for having taken the time to present it. And once again, thanks a lot from Tamil Heritage Trust. Over to you, Gauri.
Thank you so much. That was really wonderful. As Patri said, it was perhaps scholarly, but I think a lot of us can review this presentation a few times and maybe read up a little also then to understand what, especially Professor Pai's part, I think repeated viewing will make us understand what he was trying to explain. So,
you can put the slides also in the YouTube link.
Sure.
Yeah, it'll be there.
Sure. We can do that. That we can get, we can add this. So let's discuss that. We have the slides and we can add them there. Rolling.
And next month from the Tamil Heritage Trust, we'll be having our Indology Festival in the 3rd week of June. So the monthly talk is not likely to be there. So we will see you in the month of July in this monthly talk, and request all our audience to join us for the Indology Festival. The details